Hi everyone, today is our first lesson in a new unit called Rational Expressions. So first, we're going to learn about how to simplify polynomials. So I'd like you to pause the video and try this little warm-up activity, okay? Now we'll go over how we did it. So it's just a reminder about distributive property. Okay, so to go from here to this, all we did was distribute this to the 5x as well as to the negative 10y. So remember, you just multiply the numbers together. The x squared times the x becomes x cubed. Remember, you just add the exponents. And then the y, there's no other y, so it just becomes y. And you do the same thing for the second term. Okay, for the second example, you had to first notice that this 3x is only multiplying this bracket, okay? It has nothing to do with what's going on over here because it's separated by a subtraction sign. So the 3x only is multiplied by the 4x minus 5. Okay, so you expand that to 12x squared minus 15x. Then you treat this as a negative 4x multiplied by this bracket, okay? You must include this negative when you're carrying out the distributive property. Okay, so you get negative 24x plus 40x squared. Okay, and then you collect like terms to get your result of 52x squared minus 39x. Okay, so that's just a warm up to remind you of that distributive property. So to simplify polynomials, the first thing you have to do is to expand all brackets using the distributive property. So remember, a times b plus c would result in ab plus ac. If you like these arrows, you can draw them in like that. If you have two binomials, then it's the FOIL method, right? So you have f, o, i, l. So a times c is ac. So those are the firsts of the f. Then the outsides, a times d, so AD. Then the insides, B times C, and then the lasts, B times D. Okay, that's the FOIL method. Firsts, outsides, insides, and lasts. Finally, this is a very common mistake people make when expanding a plus b quantity squared. It's not a squared plus b squared, tisk, tisk, tisk. It is, in fact, can be written as a plus b times a plus b. And I often suggest students write it out this way to avoid making that mistake. And then you complete the FOIL method. So you're left with a squared, and then you get a times b is ab, b times a is ab, so you get 2ab plus b squared. Okay, so that's basically just FOIL, and then you collect the like terms in the middle there. Okay, so first you expand, then you collect like terms. Okay, so remember, like terms have the same variables and the same exponents. Okay, and you'll also need to remember these two properties, which you might not have known by these fancy names before. But the commutative property, for instance, so if something's written as AB, you can rewrite it as BA, or vice versa. It doesn't matter if it's multiplication, it doesn't matter the order it's written in, you can rewrite it in a different order as it suits. And the associative property. So if you have just a number times something, you can group the first two together and have C on the outside there. Okay, so that's the first page, just some reminders for you. So we'll do a few examples here. Okay, so these word problems also require some thinking. The horror. Okay, so we have to create some expressions. So a rectangle is twice as long as it is wide. Twice as long as it is wide. So right away I'm thinking, okay, a rectangle is twice as long as it is wide. So its its length is equal to twice its width. Okay? So when I see something written like that, I want to rewrite it as a math statement. So it's twice as long as it is wide. So its length is 2 times its width. That fits. Okay. So how will the area change if the length length is increased by 1 and the width is decreased by 1. Okay, and it's asking how the area will change. So we need to create two triangles, our original triangle and then our changed triangle, and see how the two areas compare. So we have our original triangle and then our changed triangle. So our original area is length times width, right? But we decided that length can be rewritten as 2w, so you get 2w times w, or 2w squared. Okay? Our changed triangle, now the length is increased by 1. Oops, not like. The length is increased by 1, and the width is decreased by 1. Sorry, not right. Okay, so length is 2w plus 1, and then we have w minus 1. Okay, so we want to expand this area so that we can compare it to 2w squared. So you FOIL this, so you get 2w squared minus 2w plus w minus 1. You collect like terms to get 2w squared minus w minus 1. So now we just need to compare. Okay, so this new triangle is, what do you think? Is it smaller or bigger? Well, it should be smaller because notice you're subtracting the width and a value of 1. So it's smaller by w plus 1. Okay, notice I did w plus 1 because if you were to factor this out, you'd be taking away a w plus 1. Okay, so the new triangle is smaller. So again, we made this comparison by creating this polynomial and then looking at the two simplified equations, and that allowed us to compare it. Okay? Now, the next question involves consecutive integers. Consecutive means one after the other. We did a lot of work with this in grade 9 and grade 10 with linear functions. Okay? So sorry, if I rewrote then the product twice, you can take that out. So we have 5 consecutive integers. Okay? So we're going to say let A represent the first integer. Okay, remember the fact that they're integers just means that they're whole numbers that can be positive or negative. Okay, no fractions or decimals here. So we want to prove that the square of the middle integer is always 4 more than the product of the first and fifth integers. Okay, so let's rewrite a mix of English with math here so this makes a bit more sense in our brain. So the square of the middle integer, so the middle integer squared is, anytime we say is, that's an equal sign, 4 more than the product of the first and the fifth. So the product of the first and the fifth, so that's multiplication, and then plus 4. So this is what we need to write, but with variables. Okay, I find it helps to do this middle step to connect, to make a bridge kind of, to connect to the English down to the math. So if A is our first integer, our next consecutive integer is A plus 1. Okay, that's how you get to the next number, you add 1. And then you get A plus 2, because it's A plus 1 plus 1. Keep adding 1. A plus 3, and A plus 4. Okay, so now this is our first, second, third, fourth, fifth integer. So now we just need to sub these in to this expression. So our middle integer is A plus 2. So A plus 2 squared. We want to show that that's equal to A, which is our first integer, times our fifth integer, A plus 4, and then another 4 out here. Okay, so in order to do this, we separate into left side and right side, show that they're equivalent, and then conclude that they're equivalent. Okay, so our left side here is a plus 2 squared. So that's a plus 2 times a plus 2, which becomes a squared plus 4a plus 4. Okay, because you get 2a plus 2a to give you the 4a. Okay, our right side, so be careful, make sure you do BEDMAS. You do this multiplication, okay, and you keep this plus 4 out here because it's not being multiplied by anything. So you get a squared plus 4a plus 4 on the outside. Oh look, they're the same. Yay, we did it. Left side equals right side. Smiley face. Okay, so that's kind of one half of the note about simplifying polynomials. The next part involves proving equivalence or proving non-equivalence. Okay, so proving equivalence requires a lot more work than proving non-equivalence. And this is true throughout mathematics as you continue in your mathematics. Proving that something is true is a lot harder than proving that something's not true. Because to prove that it is true, you have to show that it's true on any circumstance. Whereas if you want to prove something's not true, all you have to do is find one teeny tiny little example where it wasn't true, and then you can say it's not true, because you can't say it's true for everything. Like for instance, you can't say, oh, I never lie. Because if you find even one example where you did lie, then that whole statement is false. Okay, so here we go with our proving equivalence. So two polynomials are equivalent if they simplify algebraically to give the exact same function or expression, so you can make those equations look the exact same, or if you graph them, they produce the same graph. To prove two polynomial expressions are equivalent, you need to simplify both expressions and show they're equal. So I'll just do one simple example for this. Prove these two polynomials are equivalent. So this long one and that long one. So all you need to do is separate into C1 and C2, and you simplify. So 10n plus 20n is 30n, minus 5n is 25n. 500 plus 200 is 700. Okay? Then we get 10n plus 20n minus 5n is 25n plus 700. So then you can conclude C1 equals C2. And that's it. So really these are just the same polynomial written in two different ways. So you just need to simplify them so they look the exact same. That's all. Okay? Now to prove non-equivalence, so two polynomials are not equivalent if they result in different values when evaluated with the same number being substituted for variables in each. So that's the key. You have to put in the same number on both sides. And if you put in the same number and you get a different result in the two expressions or functions, then obviously they're not equivalent. That doesn't make sense. So to prove this, either you have to simplify both expressions to show they're different, or you can just put in values that show that the functions are not equivalent. So both of these methods have merit. You want to just kind of take a look at the problem and see which one is the simpler thing to do. So in this case, because there's such big numbers here, I think it's actually simpler to simplify these functions than it is to put in a value for t. Okay? Just because you'd have a lot of calculations. So I'm just going to simplify both. So f at t, okay, you're just collecting like terms. Minus 5t squared, and then this would become plus 5t squared. So there's no more 5t squareds. No t squareds at all, actually. 100t minus 75t, so 25t. And then 1,000 minus 1,200, so minus 200. All right? And then g at t which is there's nothing to simplify. So right away, you can see they're not equivalent, so you can just say f of t does not equal g of t. Okay. So again, you could have just put in a value for t, like let's say you put in 1 into function 1 into f, you would have gotten minus 175. If you put 1 into this function, g of t, you would have gotten 2,375. So that again would show that they're not equivalent. Okay, so substituting values is enough to prove non-equivalence only. You cannot just put in values to prove that something is equivalent. People do this all the time. Don't let it be you. Okay, if you're subbing in values, that only shows that something is equal or not equal at that one specific place. So that's enough to show that it's not equivalent. If it's not equal at that one space, then you have to say that it's not equivalent. But if it's equivalent just at that one spot, I don't care. That only shows me that it's equivalent right there. To prove equivalence, you have to show it's equivalent everywhere. Okay, and that's why you have to simplify the expression.